Hi, GOH. This is Unit 7, Lesson 8, and today we're going to talk about the side splitter theorem, which is actually pretty easy. I think you're going to like this. So in the next few lessons, we're going to be looking at specialty applications of similarity. One of the most famous and useful is known as the side splitter theorem. This first exercise will help to investigate this theorem. So I have triangle ADE, which is the big triangle, and I have line segment BC has been drawn such that it's parallel to DE, and you can see that it's marked that it's parallel. Justify why the triangles are similar to each other. Now this is something that we've been doing all along, but since BC is parallel to DE, okay, then angle 1, we did this proof, is congruent to angle 2 because they're corresponding angles. And angle 3 is congruent to angle 4 because those are corresponding angles. So angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4. They are corresponding angles. So the lines are parallel, therefore all the rules for parallel lines hold true. All right, there are corresponding angles. Therefore, triangle ABC, oops, that should be a B. ABC is similar to triangle ADE by angle. They also share angle A, all right, but I didn't need to write that because I already had two angles. So let's put some information on our picture. So AB is 6, AD, this whole segment, is 10, AC is 9, and they want me to set up a proportion to find AE, which is this whole segment right here. AE, the thing that I'm going to try and find, I'm going to call X. Now, since my triangles are similar, therefore the sides are in proportion. So I'm going to take 6, which is the top left, and I'm going to take 10, which is the whole left side, and I'm going to set them equal to 9, which is the top right, and then X, which is the whole right side. All right, because the triangles are similar, the sides are in proportion. So I set up my proportion. I cross multiply. 6 times x is 6x. 9 times 10 is 90. And I divide by 6, and x equals 15. All right, so that is AE. So AE equals 15. And they also wanted me to find the length of CE. Well, CE is just going to be AE minus AC. So it's AE minus AC. So that whole segment is 15. I just figured that out. And I subtract 9, then CE is 6. All right. Let's find the following ratios of the lengths in their simplest forms and compare. And then what do I notice? So AB, I'm going to move this down so we can see it, is 6. BD is, well, we didn't figure that out, but we certainly can easily enough. The whole segment is 10, and the top part is 6. 10 minus 6, now I know that BD is 4. And if I reduce that, I get 3/2. And let's do AC. AC is 9, and CE I just figured out is 6. That's also 3/2. The ratios are the same, so the segments are in proportion. Since the ratios are the same, the segments are proportional. Since that's true, we're going to see what our side splitter theorem says. You can also make up a proportion that just uses the top and the bottom of one side and the top and the bottom of the other side. You don't need to use the whole entire side. So we see that parallel lines segment drawn divides up each side proportionally. So here's my side splitter theorem. So the side splitter theorem right here says a line drawn to any side of a triangle that intersects the other two sides will divide them proportionally. So basically AB is the top left, BD is the bottom left. That's equal to AC, which is the top right, over CE, which is the bottom right. So you don't have to use the whole entire side. All right? So this, I'm going to skip this because this is kind of long and involved. this is just an algebraically showing the side splitter theorem by taking a proportion and we write the segments as their parts and I cross multiply and everything drops out. But take my word for it, side splitter theorem definitely works. So if we flip this over, the side splitter theorem makes solving for proportions of the sides of a triangle split by parallel lines relatively easy, as the following exercise will illustrate. So I know that RU is parallel to SV, is parallel to TW. If RS is 15, VW is 6, TZ is 25, and WZ is 15, they want me to find ST and UV. Well, I'm going to have to do two different proportions. One to find ST. So basically what I'll do is I'll use these sides that I'm highlighting in yellow. Okay, so the triangles are similar. Now, why are they similar? Because those lines are parallel, therefore those corresponding angles are congruent. Since the lines are, since the triangles are similar, then those sides are in proportion. So here's what I'm going to do. I'm going to take the 25 and the X, and I'm going to take the 15 and the 6. Now, could I have done X over 25 and 6 over 15? Absolutely. As long as you're consistent, that's fine. So 15 times X is 15X. 25 times 6 is 150. Solve for X by dividing by 15, and X is 10. Now I want to solve for Y. UV, so I'm going to call that Y. All right, and what I'm going to do is I'm going to take these segments, I'll circle them in blue, and these segments, and I'm going to write another proportion to solve for Y. All right, because the lines are parallel, the triangles are similar, the sides are in proportion, but I can just use the parts of those sides. So 15 over 10. Now if I do the 15 first and that goes on top, then the Y has to go on top, and the 10 went on the bottom, the 6 goes on the bottom. As long as you're being consistent, that's fine. 10 times Y is 10Y. 15 times 6 is 90. Divide by 10. Y equals 9. Okay? All right, problem that's a little bit harder. So a right triangle has had one of its legs divided into segments of lengths of 2, 3, and 5 as shown. Lines parallel to the other leg are then drawn to the hypotenuse AD, dividing into 3 segments. If AD is 30, then determine the lengths of AB, BC, and CD. So this whole line right here is 30. And I want to find the length of each of the parts there. Well, remember that if those lines are parallel, then those sides that have been divided are proportional. So I can just call this one 2x, this one 3x, and this one 5x, because they have to be in the same ratio as the other sides are. So this problem's a little bit different. 2x plus 3x plus 5x equals 30. I'll add up all those x's, and that gives me 10x equals 30, and x equals 3. So AB is 2x, 2 times 3 is 6, BC is 3x, 3 times 3 is 9, and CD is 5x, 3 times 5 is 15. All right, and this last problem is just saying the converse of the side splitter theorem is true. That means the opposite. If the sides are in proportion, then it would make those lines parallel to each other. So the converse means I'm just going to switch it up. Usually I say that the lines are parallel, therefore those sides are in proportion. If those sides are in proportion, then that means that those lines will be parallel to each other. So they want me just to verify. Well, I have the numbers on there, so they give me all these numbers. Those numbers are already on the picture. Verify that AB, which is 10, over BC, which is 8, equals AD, which is 15, over DE, which is 12. Okay, so 10 over 8 and 15 over 12. I can cross multiply to verify. Even easier if you don't have a calculator. Just take 10 over 8 and reduce it. They're both divisible by 2. That gives me 5/4. And take the 15 over 12 and reduce it. They're both divisible by 3. And again, that gives me 5/4. All right, I'm seeing that those ratios are the same. Is AC over AB equal to AE over AD? Well, let's look. AC over AB is 18, because I want AC, which is the whole side right here, is 18, over AB, which is 10. Let's reduce it. Those are both divisible by 2, so that's 9/5. And then let's try AE over AD. Well, AE is this whole segment. So 15 plus 12 is 27. 27 over AD, which is 15. All right, both divisible by 3, 9/5. Okay, so what's the common ratio? Common ratio is 9/5. Based on B, give a dilation that would show that ABD is similar to ACE. So basically, if I took that triangle ABD, the smaller triangle, all right, using A, this is going back to stuff we did in the beginning, using A as the center of dilation, and I dilated it by a scale factor. Remember, my scale factor is always image over pre-image. A scale factor of 9/5, then B maps to B maps to C, and D maps to E. Oops, that's an E at the end. All right, how does knowing that the triangles are similar show that the lines are parallel? If the triangles are similar, which I just proved because I could find a dilation that maps one to the other, then I'm going to put some numbers right here too. Angle 1 is congruent to angle 2, and therefore BD would be parallel to CE. So if the angles are congruent and they happen to be corresponding angles, therefore those lines would have to be parallel. So I did the reverse of what I was doing previously. All right, and that's it for this video.